Hello everyone, my name is Speck and I present today our paper When Perfect is Not Good Enough in the Search Behavior of Symbolic Heuristic Search. This is a joint work with Florian Geißer and Mattmüller. Our motivation behind this paper is that symbolic search and heuristic search are two very successful approaches to optimal planning. On the one hand side we have our symbolic planners, which usually use symbolic state representations, often in the form of decision diagrams, to compactly represent sets of states, and they usually use blind search. On the other hand, we have so-called heuristic planners, and they usually explicitly represent the states, but use informed search, like A star. And this informed search is based on heuristics, and these heuristics can be represented also symbolically as decision diagrams. Then a natural question arises, why don't we combine these two things? So take the best of those two planners, use a symbolic state representation, and also use symbolic heuristics to guide our search, and then come up with a really strong planner, symbolic heuristic planner. A short wrap up about symbolic search for optimal planning. The main idea is to operate on sets of states, not on single states. So basically we can represent a subset of our state space, so a set of state S, by its characteristic function. So for example, the formula X is the characteristic function, represents the whole set of states where X is true, and then we can manipulate this set of states by transforming the characteristic function. So for example, the intersection of two sets of states is basically a logic AND between these two characteristic functions characterizing these sets of states. And usually, as I said before, we use some decision diagrams here, binary decision diagrams, to represent these formulas. So on the bottom left you see the BDD representing the characteristic function X, so basically all the states where X is true. And then right hand side you can see how this symbolic search performs. So we start with our initial state, and then we generate all the successor states reachable with cost 1 and so on, and we get a lot of sets of states. And yeah, what's crucial here is that the search performance highly depends on the size of these BDDs. So how large are those decision diagrams? So how can we now do symbolic heuristic search? Usually we use some A star version called BDDA star. The main idea is, given a set of states, we can split it according to its heuristic values, and these heuristic values we have pre-computed, also represented as BDDs. So here you can see first we split our set of states S with all this, we do an intersection with all the states which have heuristic value 0, for example, and we get a new set of states only containing these states with heuristic value 0, and you can also do that with heuristic value 1, 2, 3, and so on, and by this to split your sets of states into sets with the same heuristic value. And by this you get some kind of BDDA star. So we start with our initial value here with G value 0 and let's say heuristic value 2. Then you expand that and you get a lot of new buckets, all with the same G value but with different H values. You expand the one with the smallest G value and the smallest H value. Then you expand the one with the smallest G value and the smallest H value next. And by this, more or less, you expand different buckets with different F values, and the main advantage here is that you can skip some of the states, so you have to expand fewer states. So what's the idea behind that, or the performance? It's more or less that if we use a consistent heuristic, we reduce the number of necessary state expansions, so we expand fewer states in our search. However, this heuristic pre-computation to represent it as BDDs is expensive, and also to do these intersections, so this evaluation which state belongs to which bucket, is also expensive. This was known before. However, what we also investigated or observed now was that only because we have fewer states, it doesn't mean that our BDDs become smaller. So if we represent a BDD which represents the state set S prime, then this BDD can be strictly larger than a BDD representing the superset. So throwing away states doesn't mean we get fewer BDDs, smaller BDDs. And that more or less means that the symbolic search, or the search performance of symbolic search, is not directly correlated to the number of explicit states we have to expand. So expanding fewer states doesn't mean that our symbolic search performs better. So what are here the theoretical results, or we put that to the extreme. So what we showed that splitting our BDDs according to heuristic values can increase or decrease the size of the resulting BDDs, and in the worst case exponentially. So using heuristics can make our BDDs exponentially larger. And the really interesting thing here is, even if we use the perfect heuristic, so even in the best circumstances, our BDDs can become exponentially larger than using blind search. What's the main idea behind this? So let's see here, we have here the BDD representing all the states where the variable Z1 is true, and it's really compact and small. But if we now do some unfortunate intersection with a heuristic, we throw a lot of states out of this state set, and our BDD can become exponentially larger. And that's basically not what we want, because as we said before, our search performance really depends on the size of our BDDs. So that means we can have an exponential increase or decrease, here in this case now, decrease in search performance, because we use the perfect heuristic over non-heuristic. So we do all this hard work to pre-compute our heuristics, and even if we get the perfect heuristic and do this intersection, which also takes time, then our BDDs become larger and our search performance decreases even more. So we have no guarantees that using a heuristic helps us, and it can really harm our search. So we also looked at empirical results. So does this theoretical result also carry over to empirically? So for that we used BDDA star and some fraction heuristic, so basically the perfect heuristic, and then we multiplied this perfect heuristic with some constant, and we use different domains from the IPC. So here on the right hand side you see the cumulative size of the BDDs we obtained during this doing a forward search, and in blue you see the sizes with blind search on the bottom side with the perfect heuristic, on the left side with heuristic search. So if one of the points is above this diagonal, you can see that using the heuristic increases the size of our BDDs. And on the bottom you can see that using the perfect heuristic or some fraction heuristic decreases the size of our BDDs. So it turns out that in practice often the heuristic decreases the size of our BDDs, but as we showed before, theoretically there is no guarantee. And I mean, this means we do a lot of work and almost have perfect heuristics, and even then our BDDs doesn't really decrease, or we don't get a faster search. If you look at the runtime on the left hand side, you see the successor generation, so basically computing the image, and that really depends on the size of our BDDs, and there we can see that the picture is mixed. If we don't have the perfect heuristic, then our computing the successors can really be harmed by using one of the heuristics, which are, even if you use a perfect heuristic, it's quite good, but if we have not this perfect circumstance, then you can see that symbolic search the performance can really decrease if you use heuristics. On the right hand side you see the overall runtime, so also with this known bottleneck of splitting or evaluating the state, so doing this intersection with the heuristics. So there you can see the picture is really mixed, and it does not really help to use even the perfect heuristic, and we didn't consider here the pre-computation of the perfect heuristic. So if we had to pre-compute our heuristic, this picture would be much worse. So we got similar results for symbolic bidirectional search. So it turns out also in practice, using heuristics doesn't really help the way we used it before. So what's the conclusion? What was known is that heuristic computation and state evaluation are expensive, but we also showed that the BDDs can become exponentially larger by using heuristic, even under the best circumstance if you use perfect heuristic. And overall, I mean the overall target is to have small BDDs, but smaller states doesn't mean smaller BDDs. We have similar results for uniform and bidirectional search, and the take-home message is heuristic does not pay off in general, but we need to come up with smarter ideas to get smaller BDDs. For example, to partition over BDDs to obtain small BDDs, but just using heuristic doesn't pay off in general. Thank you for your attention.